There you go. Now it should be recording. So I'm going to talk about history a little bit, and then some concepts. We'll see how things go. Now, historically, if we go back to where things started, related to the topics we are going to cover in this course, uh, the history of dynamics is a mix of a little bit of, not a little bit, a lot of astronomy. What happened in astronomy back then, long time ago, and a little bit of obviously mathematics and geometry. So it's a mix of both, formed what we actually know now as dynamics, or at least what we study as dynamics. That helps us to design different systems in engineering. Now, so if we go back all the way back, I would say, let me put a title there, or at least try to do. Yeah, I can do better. So history, a little bit of history. So I would say around 1500, year 1500. I don't know the exact time. You can start by thinking about Copernicus. As I said, it's kind of related to astronomy. So Copernicus was the person who basically, or at least historically, is believed that he was the person who suggested the sun is the center of the solar system, and basically that created an ongoing, I wouldn't call it conversation, a lot of controversies for the next 100 years. So I believe we can start with Copernicus if you want to look at the history of dynamics around 1500. Oh, he said the sun is the center of the solar system, against whatever belief at the time was accepted, like the Earth is the center of the solar system. So he was the one who suggested something different, and it created a whole controversy, I would say, for 100 years. And now, fast forward about 100 years later, right, Tycho Brahe, or Brahe, depending on who you talk to, it's a Dutch name. He was actually a mathematician, right? And I think I can just put it his last name. It's about 1600, and he was a mathematician. Copernicus was Polish, actually, so if you care. But mathematician, that's not how you write mathematician. So what he did was he was doing observations. He did observations for 20 years and trying to prove that the Earth is the center of the solar system, which he couldn't, obviously. But his observations gave a lot of information about how objects or planets and stars move with respect to different planets in the solar system. That was a kind of pioneering work. It didn't really suggest that much because he was trying to prove Copernicus wrong. But while doing that, he basically provided a lot of good information. Again, moving forward, the one probably most of you know is Kepler. Right? Kepler. It's also about 1600. I have to double check. Probably 1609. 1609. Right? And he actually was working with Brahe. He was like I wouldn't say student, but he was working with him. He's famous. Right? If I don't know how much you know about planetary system and what's going on there, but he came up with three laws, like three laws of planetary motion, or Kepler's laws. Uh, I'll just put it here: three laws of planetary motion. If you're wondering if my handwriting is going to get better, I'll just disappoint you right now and say it usually gets worse. I'll try to keep it at least to this level. So Kepler, he had three laws. I believe the first one was something along the line that every planet's orbit is an ellipse with the sun at its focus, or at the focus, right? At one of the focuses, or if you think about an ellipse. But the famous rule that I guess, not the famous, second and third both are very practical, but the second one that we care and is kind of related to dynamics was the whole idea of, he basically mentioned that a line joining the sun and a planet, if you think about the sun and a planet rotating around the sun, the line joining the sun and the planet, it sweeps out equal areas in equal time. Now, translation of this law would be the statement of conservation of angular momentum that we'll see later on in the course when we start talking about momentum methods. So it was kind of initial version of conservation of angular momentum. Now, again, moving forward, I'll just give you some general idea about what was going on before. We get to Galileo. Galileo is someone that you all know. So, and this would be, I would say, the fundamental to engineering mechanics and especially dynamics in mechanical engineering. He's I would say, findings, although not as important as Newton's, we'll get to. But Galileo, well, basically, I believe 1610, so it was close to 1610, 1620, somewhere around that time. Now, what he did, he was the first person who used a telescope, I believe. So he used a telescope and looked at Jupiter and saw basically 4 moons. And then from there, he made a couple of conclusions. Again, we're not going to go into details. It's not a history class. I'll just give you a general idea. Moving forward, we get into, so these are related to astronomy. Right? These are basically astronomers, a lot of them, or at least first 3. Mathematicians / astronomers. At that time, you were a man of multiple sciences, I would say. But in terms of more close to geometry, if you move forward, Descartes was the person who we owe him the whole idea of kinematics and how to study, or studying position, velocity, and acceleration, because he studied geometry, right? And he come up with Cartesian coordinate system, right? XYZ coordinate system that we know nowadays. So imagine without that, how could we actually look into position, velocity, and acceleration? So the second, I would say not second, the next important person is Descartes. I hope that I write his name correctly. Might be there's an ES at the end. Double check. About 1630, I think 1640, along that line. So he came up with, let me just put it here. Came up with Cartesian coordinate system. Right? And again, you can look at it as when the whole idea for kinematics started. Once we have the Cartesian coordinate system, we can start defining position of an object, then take derivative with respect to position, get velocity, take derivative, get acceleration. So the whole thing started from there. Next, we'll get to the most important one, I would say, and it's Newton. Right? We'll talk about the real laws of motion. You actually talked about it in previous course of statics, and you kind of know what those laws are. And in statics, we're more focused on the first law and the third law. Dynamics, we're going to be more focused on the second law and the third law. Right? I'll talk about those when we get to force, mass, and acceleration after we are done with kinematics. We kind of follow the timeline, the historical timeline in this course. So we talk about kinematics. We start from Descartes, and then we talk about force mass, acceleration, how they are connected, like F equals to ma is Newton's second law, which is the next person, important person, I would say, Newton, and I believe it was 1666. That you already know, 3 laws of motion. Right. We'll talk about Newton, and we'll start looking at laws of motion, and then Euler or Euler, you know, who we talked to again, was the next person who was also a mathematician, at least mainly, about 1707. I should have that date. I can double check with you. I'll double check that and give you the right number. 1707, 1783. Right? Just that's actually more close to current, so we actually have better information about that. So what he did was Newton's he mainly focused on energy methods. I talked about angular momentum, torque. Well, not probably energy method. Energy method is what Lagrange talked about. But Euler was mainly focused on, or what he brought into this field was talking about angular momentum and torque. Those methods, angular momentum methods. What we said as a derivative of what the second law of planetary motion is. So Euler was more focused on that, and he was trying to study the motion of objects using angular momentum, right? As opposed to Newton, that was more focused on you know, Newton's laws and the relationship between force, acceleration, and mass. So we follow the same order. We talk about kinematics, Descartes. We talk about Newton's laws of motion. And then we also talk about Euler and Lagrange, hopefully, angular momentum and energy method. So the next person is Lagrange. You have heard his name in multiple fields. He was, again, a mathematician, but at the same time, right, coming up with rules useful pretty much for every engineering field. 1788, I believe. And that's when the whole idea of using energy method become, or he popularized that, or he advertised, or came up with that, I will say, the energy method, and how to use energy method to come up with the equation of motion. Right? So I'll put energy method. This one we can put angular momentum method. Right. So we go from Descartes, kinematics, to Newton, to Euler, angular momentum, and Lagrange, energy method. I believe we probably, yeah, exactly, we're going to follow the same order, so it should be like historically even we are correct. So we talk about kinematics first, then we talk about Newton's method, or as they call it, direct method, to derive the equations of motion. Then we go to Euler and Lagrange to talk about angular momentum and energy method to find the equation of motion. So what is the equation of motion? As the name says, it's an equation that describes the motion. Right? Remember, what is mechanics? We talked about it, or you heard about it in statics. Mechanics as a science is a science that describes and predicts the conditions of objects or matter, or I would say object is a good general form, or bodies, better to say, and whether those objects or bodies are at rest or in motion. Right? That was the whole idea of mechanics. And mechanics could be mechanics of rigid bodies, mechanics of flexible bodies, mechanics of fluids. You know, there are subsections. Now, these methods help us to do that, to describe and predict the motion. How do we do that? Once we come up with the equation of motion, the equation that governs the motion of a body, then we can use that equation to describe how it moves and also to predict how it moves. At any given time, let's say you want to know where this specific object will be if it's given some initial velocity or acceleration. So that's the whole idea. They give us this power to study the motion, right? Whether it's law through Newton's laws or direct method or angular momentum or energy method. Each has its own way of coming up with ways to find those equations of motion. It's a little bit of history. Again, if you're interested, I actually put more detailed document. I would say document that lists more detail. I would say historical events and people who influenced or had some effects on dynamics as a field. Right? You can take a look at that article if you're interested. I just put it there. It's really nothing. There's no exam on it or there's no question on it. But if you're interested, it gives you a pretty good and way better than what I just said and more accurate than what I just said, a good view of history of dynamics and what everyone contributed and how things went, specific quotes. If you have time, it's the beginning of the semester. So if you have time, I highly encourage you to just take a look at it. It gives you a better sense of where we are. As they say, we're standing on the shoulders of giants. These people pretty much contributed a lot, and each, yeah, I'll just put it there in case someone's interested. All right. I usually say if there is any question, but I mean, still you can ask a question, but I'm assuming it's a history. So early morning on Monday, on Thursday, talking about history. If I haven't lost half of you, I would consider myself lucky. All right. So let's talk a little bit about some fundamental concepts, I would say. Not fundamental concepts. I would say three things. Let's just establish the definitions: position, velocity, and acceleration. You already know what they are, right? You've become familiar with them in physics. I'll just do a quick review before we dive into how to study the motion of a particle. So let's put the title as position. For the lack of creativity, I'll just say position, velocity, and acceleration. Now keep in mind, before I get into defining these, we have to define, as they call it, a reference frame. What is a reference frame? Well, as the name kind of insinuates, that it's a frame of reference that you make your measurements with respect to it. Think about a coordinate system, an XYZ coordinate system. When you want to say where something is located, a good example would be think about your own room. And imagine that you put the coordinate system in the corner of your room. Now, anything in the room, like your books, your computer, your, I don't know, whatever you have, picture frames, you have, whatever you have in your room, when you want to indicate where it is, you can refer to that with respect to that coordinate system that you put in the corner. You can introduce a Cartesian coordinate system that its axes are aligned with the walls of the room, and then you can address the position of everything in your room with respect to that. That's the general idea of a reference frame. You need a reference frame. You need something to address the position of objects with respect to it. Now, this reference frame can be stationary, like in your room, which technically is still not stationary. Your room is part of the country, which is part of the planet, and it's rotating, but relatively speaking. Or it can be moving. Imagine if you're on an airplane and you want to refer to something in the airplane, like the seats in front or the person sitting at a specific place, third row from the back. Right? You have to put your reference somewhere. So the reference frame is at the end, for instance. So when you refer to something in front. So that reference frame, that frame is your reference frame, but it's kind of moving in that case, right? Because it's attached to your plane. We'll talk more about relative velocities, relative motion, way in the end, closer to when we start talking about rigid kinematics of rigid bodies. But we have to have a reference frame. Right? So I'll just put it under the definition of, maybe it's better if I change this to. So let's say reference frame. If I want to be accurate, I'll say a coordinate system. Now, this coordinate system can be Cartesian coordinate system, as introduced by Descartes, or it can be polar or tangent normal. We'll talk about those coordinate systems. A coordinate system that is suitable for I would say specifying, maybe that's the word the text will use, that's what I remember, for specifying the positions of points. Right? Very simple. You know it from math, you know it from geometry, you know it from physics, you are familiar with that. In a very simple form, right? If you think about that, is definitely out of size. If you think about a frame like this, I'll just put it here for us to have a picture of what's going on. Right, let's say this is, I don't even care, just the center, origin. I'll call the origin O. And let's say I have a point here, P. If I have a reference frame, right, I can define a vector that describes the position of this point in this reference frame. I'm going to define it as R. That's what we're going to go with in this course. So this is R. Probably I should have used it. This is R. What does R do? R, to simply put, R describes the position of a point in your reference frame. So R does nothing but describes the position of a point. Now, if the point moves, which is pretty much what happens in dynamics, things are moving as opposed to statics. Right? Not as opposed to statics, things could move too as long as the acceleration was constant. But a little different from statics, things are moving. So when the object moves, R becomes a function of time. What do I mean by that? That point P, you can think about it if it goes, let's say, this way at any given moment. So if you want to draw the vector R continuously at any given moment, R changes. These are all point P is just moving along a line, specific path, whatever line is that. So again, simple concepts. When the object or point, object/point moves, then R as a vector is R a vector as a function of time. Right? At any given time, R gives you where that point is. Yeah. Fundamental concepts we're defining. Now, if you want to define velocity, right, this would be the position. I'll describe the position. Now, if I want to define velocity, velocity would be the rate of change of the position of P. very simply put, velocity would be the rate of, I can do it by the rate of change of the position of P. I can define it as V. You can look at it this way. V as velocity is equal to dr dt. And you know, derivative is basically, if you go back to the fundamental definition of derivative, is basically a limit, right? Limit RT plus delta t minus RT divided by delta t. Again, you can add more. You can say this is the this is basically a definition of displacement. Of displacement, which is pretty much nothing but change in position. And this is time interval. So I should say delta t goes to 0. Okay. Pure mathematical definitions. We're defining velocity now. What is the unit for velocity? Remember, we had 4 basic quantities in mechanics and all the way from statics. We had time, space, which we represented with length, time, space, mass, and force. And we said 3 of these 4 quantities, basic quantities, we define units for, and the 4th one, its unit is defined based on the other 3, depending on if you are in SI system or US customary system. Now, this case, we have velocity, we have length. So if you think about the unit would be distance or length, better to say, the unit of length, whatever is that. Basically, displacement is nothing but length divided by time. So the unit could be pretty much any unit length for any unit for length over any unit for time. Could be meter per second, feet per second, inch per second, kilometer per hour, mile per hour, right? Depending on what unit you use for length and what unit you use for time, right? So we talked about position. As long as we have a reference frame, we can define the position, pretty much where that point or particle at this point is located. Remember, we're only focused on a particle. A particle is an idealization of a real object. A real object, the difference between a particle and a rigid body or real object, I'll talk about later on, the end of the semester, closer to the end of the semester, or last 5 weeks, I would say, is that a particle has a mass. What we don't care about is geometry and how the mass is distributed. A rigid body has mass, and we also care about how that mass is distributed in its geometry. We care about its shape, and that's a rigid body. Now, which one we choose? Well, it's relative depending on the size of that object with respect to everything else in our system that we're studying, depending on what our purpose of the study is. Idealization, obviously, idealization of a rigid body as a particle has its own benefits, makes your life much easier in so many cases, but it comes with some, obviously, shortcomings. But for the good portion of the semester, we'll be focused on particles, and I refer to them here and there as points. And you might also see it in your textbook. So point and particle, at least within the scope of this course and what I talk about, are interchangeable, and I use them like interchangeably. It doesn't really, there is no difference. All right, so How about acceleration? Now we have acceleration. These are the components that we need to study the motion of a particle, which is basically the topic of the next topic that we're going to be focused on. Now, acceleration, easily we can just define it the same way. It's the rate of change of the velocity of p. We can just call it acceleration. So the rate, I would say rate of change of the velocity of p. All right, you can define it with a. We define it. I have to put the vector there. I forgot that. Acceleration is also a vector. Right? It would be dv, it's a vector dt. Again, you can just go into more fundamentals. V, one of the things you're going to see, unfortunately, we use V for velocity. We use V for a few more things in this course. So at this point, it's good, but later on, I'll try to keep emphasizing what V we use it for. Also, the energy method we get for different naming. But for now, we're good. So V, T plus delta T minus Vt over delta T. The numerator is basically change in velocity. The denominator is time interval of time. And for units, again, we look at what we have there. So it's distance or length. Let me be consistent. Over time squared, if you think about it, because V is length over time, and then you have divide that by time, so it becomes length over time squared. And anything that fits into this category, so meter per second squared, feet per second squared, inch per even minute squared. You can go with anything pretty much, as long as you have the right you have a unit for length and you have a unit for time. Obviously, the standard one in SI system is meter per second squared, and the standard one for velocity in SI system is meter per second. But any combination you might face, and you might end up converting things. Kilometer per hour squared, mile per hour squared, any combination of these. So we got our definitions, right? Reference frame is something you need to have a reference to measure the position. Once you measure the position, again, the position is changing typically for a particle that's moving. Even if your reference frame is fixed and your particle is moving, your position is changing as a function of time. Since it's changing as a function of time, you can take derivative with respect to time, and that gives you the velocity, basically rate of change of the position. And we can take another derivative, which is the acceleration. Technically, in physics, we can take another derivative, and we don't really deal with that in engineering, but that would be a definition of a jerk. Right, it's going to be meter, basically the rate of change of acceleration. You've probably heard that in physics, or you might have heard it in physics. Basically, rate of change of the acceleration, and the unit would be meter per second cube, feet per second cube. We don't really deal with it, so we don't even talk about it. All right, I'm just going to stop here. We'll talk about motion on a straight line in the next class, and then we'll go over examples. When we talk about motion on a straight line, we'll basically use the same concepts, but what happens is that we are restricting the motion of this particle to be on a straight line. So things become simpler, or simple, relatively speaking. We start from there, and we look at different types of accelerations that you might have. Acceleration can be a function of time, can be a function of displacement, can be a function of velocity, and how can we deal with those cases. I'll go over a couple of examples, hopefully. In next class and the class after, we'll see how things go. And then we dive into when the path is not straight. And we have a curvilinear kind of motion. We'll talk about that. That would be probably 2 classes talking about polar systems, tangent normal system, and how they are formulated. But everything starts basically from position, velocity, acceleration definitions. All right.